the periodic table you are seeing today is quite recent form. Previous one, we have several one who proposed different table. So we will look the main contribution to see how the table has been established. Then we talk about the effective nuclear charge. Why that? Because we know in the electronic structure of atom that one atom is constitutes of one positive nuclei, which is very heavy, small but heavy, and the electron which are negative, teeny, no dimension, point lines, but keep moving all the time, and then generates the volume of the atom. So when you learn physics, classical physics, you know very well that when you have a positive charge and a negative charge, you have an interaction. But at the same time, in the electronic configuration, you understand that in one element, in one atom, you have several electrons. They are not arranged in the same layer. They are arranged in different orbital with the distance, with different distance to the nuclei. So now the question is how the outermost electron will be interacted with the positive charge. So we talk about the effective nuclear charge. And then we talk about the size of the atom and the ion, how the size will be changed when one atom receive one electron to become an ion, or remove one electron to become cast ion. So in this case, what could be the size of an ion compared with the size of the neutral atom? And then we talk about the energy that will be required to provide to atom to remove one electron, because the atom is stable at the ground state because the electron and the nuclei have interaction to keep the electronic structure stable. It says that they are at the lowest energy level, potential energy point of view. So now if you want to remove one electron, you need to bring this electron, you need to break the binding between the electron and the nuclei. So in that case, you need to put energy. So what could be this energy, the energy you need to put in? We call the ionization energy. The same thing, when the atom receive electron, it will also, because the electron is negative charge. So if you want to send a second electron to form a pair of electrons with this electron already exists, you need to pay energy. So in that case, you have electron affinity. Okay. So back a little bit about the discovery of the element. That's also the driving force for the establishment of a periodic table of elements. So very far in the history, in the ancient time, the number of elements that people know are very limited. For example, they know only about 3 elements: silver, copper, and sulfur. So when the number of elements are limited, you can imagine that one can remember the chemical and physical property of each element. When you have only 3 friends, you can remember the name, the character of each of your friends, okay? Easily. But then by the early of 19th century, people already know about 33 elements. So now the number of elements increased drastically. It also say that you still can remember very well one by one, but the number of people that have good memory, good capability to remember the chemical and physical property of all 33 students, 33 elements will be quite limited. So only very smart guy can remember. I assume that I cannot remember 33 elements like this. And then in the second part of 19th century, the number of elements that has been discovered become 63. So with 63 elements, for sure that very few people can remember all the physical and chemical properties. Okay. So now, how you can work out, how you can play, how you can exploit the element, because when you learn physical and chemical property of element, it's not for fun. You learn the physical and chemical property for creating a new object from the element with the property that you want. But if you don't know the chemical and physical property of the element, very likely that you cannot invent something new from them. So now, if you put 63 elements by a way like random like this on the slide, only few people can remember. So that means only few people can invent something new based on the element. It also say that the progress of the science and the progress of technology will be very limited. So more people can learn and can know about the chemical and physical property of element, better chance the society will have to invent, to develop something new for the best of the human being and for the development of the society. So people start to say, now you have 63 elements randomly like this. How can we arrange in a structure, in a table, thus you will have a group element which have comparable physical and chemical property. In that case, when you can classify the element, when you can put the element in different groups with different chemical and physical properties, so people can easily to remember not all the elements, but remember the physical and chemical property of each group of elements. Okay, so that's the purpose. People to start to think about the need of arrangement of the element in a table. So with this request, in 1869, Mendeleev in Russia and Mayer in Germany, they independently proposed idea of periodicity. That means the property of element will repeat after few elements when they put in a table. So here is something in Vietnam we know about the periodic table of element proposed by Mendeleev. But remember now we have to say that at that moment, both Mendeleev and Mayer in Germany, they proposed the same idea. That means they independently proposed the idea of periodicity of element. It say the similar chemical and physical property recur periodically when the elements are arranged in order of increasing atomic weight. How is it? So you have here a list of elements, you have symbol, and you have atomic mass. So try to put the element in increasing of atomic mass. You will see that the chemical and physical property of the element repeat at some instance. For example, here is the historical Mendeleev table. So you put the mass increasing by following. So you start from here and the mass increasing by this. Huh? Okay. So you will see that it will have a group of elements With hydrogen, lithium, sodium, potassium, they have comparable physical and chemical property. They are very soft, easy to be cut, except the hydrogen. They react violently with water and with oxygen. When you put it in exposed in air, they will burn. They are flammable. And then you will observe also a group of carbon and silicon. They are quite comparable in terms of chemical and physical property. So here is the first table proposed by Mendeleev based on the increasing of the atomic mass. So the table of elements advanced by Mendeleev and Mayers were the forerunner of the modern table. In the case of the table proposed by Mendeleev, the group element according to property, for example, you have hydrogen, lithium, potassium, and sodium in a group, and it can predict the property of element which has been not yet discovered at that time. When you propose a theory, you need two requirements. You can satisfy two things. First, your theories can explain the property already exists. The experimental data already discovered. That's the first thing. If you cannot explain all the experimental data already found, that means your theory is still quite limited. The second requirement is that your theory can predict the next experimental data. Okay? In that case, when people generate a new experiment data and they fit very well with your theory, that means your theory have excellent value, excellent contribution to understand the phenomena. So the table of Mendeleev have to group the element, different element, 63 element in different group of element, where in each group the chemical and physical property are comparable. Mendeleev can predict the property, physical and chemical property of element which has been not yet discovered at that time and discovered later and found that they are the property quite similar to those predicted by Mendeleev. So here you go. Mendeleev predicts an element he called Ica silicon. That means an element similar to silicon. And then after that, they discover an element which is germanium, discovered in Germany, named germanium. And you can see here the atomic weight predict is 72, and actually the weight of the germanium found is 72.95, 59, sorry. And the density is quite similar. The specific heat similar. Melting point, Mendeleev say the melting point is high. It's quite difficult to estimate what I mean high, but actually the germanium melting point is 947, so actually it's very high. Mendeleev predict the formula of oxide is XO2, and the oxide of germanium is germanium O2, exactly what predicted. The density of oxide is exactly identical. Formula of chloride is also exact. Boiling point a little under 100 is what Mendeleev predicts, and actually the experimental boiling point of the chloride is 84. So it's quite close, consistent predicted by Mendeleev. So you see why here start to putting the element in one table, they can explain the similarity in the physical and chemical property of several elements in different, and then they can also predict the chemical and physical property of element which has been not yet discovered. So that's why the contribution from Mendeleev and Mayer were extremely important to the development of chemistry. So here is a summarize the table of element where you see the date of discovery of different elements. Okay. So very recently, in 2016, 4 new elements, 113, 117, and 118, has been added into this element. So now you have a complete element, a periodic table of element. However, the Mendeleev table have some issue. Remember that this table is established based on the atomic weight. So Mendeleev proposed that you contract the table by putting the atom in increasing of atomic mass. However, by putting like this, you will have the few cases which are not consistent with the property. For example, you have argon with the mass is higher than potassium. So it says that if you put increasing of the mass, this position should be potassium, and then this position should be argon because you put the mass increasing by this guy. Okay, and then because the potassium has smaller mass than the argon, so normally you should put potassium here and the argon here. However, you see that the potassium have chemical and physical property similar to the potassium to the sodium and lithium, but not like crystal and neon. And you see also that the argon have the same noble property, inert character, like the two elements. So if you put in the mass increasing, this position should be potassium. But we are talking about not the mass of one element is physical character. Here you are interested more in the chemical character. So the chemical property of the argon are close to the of neon and crystal, and the chemical property of potassium is very close to the sodium lithium. So basically here you inverse the order of the atomic mass. So you put the lighter after the heavier one. So the real one, you put the potassium here, but not the argon. Okay, so you see there's some exception based on the atomic weight proposed by Mendeleev. So, as we discussed in the last lecture, we know that X atom have one atomic number, and X element experimentally produce one unique X-rays footprint, X-rays pattern. And the atomic number is the number is equal to the number, identical to the number of proton inside the nuclei. So now, if you put the element in order of increasing atomic number, but not in the increasing of atomic weight, like proposed by Mendeleev, then the problem, the issue you found for argon and potassium will be solved. So that's why they do the modification of Mendeleev table by using the atomic number of element, but not the atomic waste anymore. So historically, Mendeleev proposed the table of elements based on increasing of atomic mass and atomic waste. But then you will see some issue like the K I explained, argon and potassium. So when you try to change, people try to change a little bit by using the atomic number, but not atomic waste, then the problem of potassium and argon, this issue like that will be solved. So now the reason the model periodic table of element is constructed at a place by using increasing of atomic number. So some may ask question, what could be the atomic X-rays? Because we say that it's characteristic for X atom. So basically, remember that you have here so you have here a nuclei, okay? And you have a multi-electron which ranks in different, which arrange in different layer. So the inner layer, the first layer we call the layer K. The second layer, layer L, and the next one is layer M. Of course, the distance of electron in the layer K to the nuclei is shortest. So the interaction between the electron and the nuclei is strongest one. And then the binding energy between L layer and the K layer. Now, imagine that you have incident radiation, which bring energy, which is higher than the binding energy. In that case, the electron of the K cell will be ejected. So that means you remove the electron from the K cell. Then here you have one electron which been position of one electron will become empty. That means this layer of K lack one electron. So what will happen? The electron from the second layer L will fall down to fill this position. And because it have a higher potential like energy like this, so here you have the K, you have L, and you have M. Now it's become ejected. So it's empty. So the electron here will fall, and when it fall down, it will emit the radiation. So it will have X-ray emitted. The electron here also fall and then emit the second X-ray. So you see that with X atom, when you remove the K cell electron, you will have a several pattern of emission, X-ray emission. And this emission X-ray is characteristic for X atom. You will not find two atoms with the same emission, with the same X-ray emitted pattern. Okay? It also means by measuring the emitted X-ray, you cannot confuse two atoms. Now, we move to the effective nuclear charge. If we sometimes mention, many of the property of the atom depend on their electron configuration and on how strongly the outer electrons are attracted to the nuclei, as I mentioned. So you can imagine that the outer electron, which is far from the nuclei, if they bound, the can be easily to remove. Later, when you learn the general chemistry too, you can say in that case, the atom, the element can be easily to be oxidized. That means remove electron. So you can see that the property depends strongly on how the interaction of the outermost electron, outermost layer of electron interact with the nuclei. The force of attraction between an electron and the nuclei depend on two things. First, the magnitude of the net nuclear charge acting on the electron, and the average distance between the nuclei and the electron. Why we say about the net nuclear charge acting on the electron? So imagine that you have here one atom. Here you have positive charge nuclei, and we are talking about the outer layer electron here. Okay, so you have interaction of this electron with the nuclei, one negative charge and one positive charge. But also in between the electron and the nuclei, you have a second layer of electron. These electrons have a negative charge. So the interaction between the electron and nuclei is attractive force, attractive interaction. Why the interaction between the negative charge and negative charge here between the electron and electron become repulsion interaction. So the total interaction of the electron and nuclei is a kind of the total between attractive force between the electron and nuclei and the repulsive force between the electron and electron. You can imagine that you have a positive charge here. If you have more electron which mass the outer electron, then the interaction between the nuclei and the electron will be weaker. If you have 0 electron here, in between the electron outer and the nuclei, the interaction and so as in the case of proton, you have only one electron and one proton. Atom, hydrogen atom, you have only one electron and one proton. So there is no electron that mass the interaction of nuclei and electron. So in that case, the interaction will be maximum. So by definition, the effective nuclear charge is the net attraction of electron to the nuclei is combination of the interaction with the average environment created by nuclei and the other electron in the atom. So you can imagine following. If you take the effective nuclear charge, this is the net positive charge of the nuclei experienced by the outer electron is when equal to the nuclear charge is number of the proton in the nuclei, and S representing for shielding or screening constant is always greater than 0. Of course, for the case of hydrogen, it's going equal to 0 if you want, because no electron shielding anymore. But for the many electron element, the shielding constant, screening constant will be greater than 0, but less than S. In the case this constant equal to Z, that means this effective nuclear charge will be 0. So it will be never exist. It never exists the 0 effective nuclear charge, because whatever the number of the core electron, the electron inside you have, even is many electron, core electron you have, the outer layer electron will all the time experience, all the time feel the positive charge of the nuclei. Otherwise, it's already removed. If there are no interaction with the nuclei, of course, you can imagine that the outer layer can also already fry out. So it say the S result, the S value will be all the time larger than 0 and smaller than S. Okay, so this all the time bigger than 0. That's the meaning. For example, if you take the K of sodium, you have 11 electrons. You have 10 electrons in the core because sodium electron configuration, you can draw like Leon and 3s1 like this, okay? So the outer layer electron, will be electron 3s. And inside, you have 10 electrons, okay? And sodium, you have Z main number 11. So that means you have 11 positive charge. So you have 10 electrons will be in the core, which screen the outer layer electron here. So in that case, the effective nuclear charge equal to, if you just consider the 10 electron inside and 1 electron outside, so you can say that the positive charge experienced to this outer electron will equal to 11 minus 10, right? And equal to 1. But actually, this electron outer layer will feel all the time more than 1 positive charge experienced to it. The reason is, imagine that if the 3s electron only stand outside like this, then the nuclei here, okay, will be masked by 10 electron here. And you can see that's positive 11 minus 10 equal to positive 1. That means the outermost layer electron, 3s electron, will feel 1 positive charge experiment on it. But when you look at the size distribution, the size of the 3s orbital, you see that 3s orbital, 3s electron have high probability to stand in this area, outer layer. But it have also probability to find electron here, close to the nuclei. So that means sometimes electron will get close to the nuclei rather than stand outside in the 3s layer. So when it gets closer, the interaction with the nuclei will get stronger. So that is the reason the net positive charge, the effective nuclear charge experienced to the outer layer 3s electron will be greater than 1. Is it clear to you? What I mean is that if it stands only outside, far from the nuclei in this area, this one, then the should be 1. Okay? But because sometimes this electron moves here, so here, of course, you will have stronger interaction with nuclei. So at the end, this one, you will have Z effective larger than 1 because you will get stronger interaction with the nuclei because you get closer. So if you look at the carbon atom, so you see that the carbon atom we have, it will have the electron configuration 1s2, 2s2, 2p2. The energy of the orbital 2p is higher than the energy of orbital 2s. Even both 2s and 2p stand in the same cell, n equal to 2. An electron in the 2s orbital is less effective screens or sealed by the core orbital than an electron in the orbital 2b. Because you see here, it's quite easy to imagine. Electron 2s have probability to get closer to the nuclei compared with the orbital 2b. Orbital 2b, electron orbital 2b, they get further to the nuclei, so they will experience less positive charge of nuclei effect on it. So, in the periodic table of elements, the effective nuclear charge increase as we move across any rows of the table. The effective nuclear charge increase as we move across any rows of the table. If you're going down a column, the effective nuclear charge experienced by a valence electron changes far less than is done across the rows. That means when you consider the effective charge of the element in one row, the change is more significant than you consider it change in one column. So let's say now we move to the next, the size of atom. So here, if you see in this demonstration figure, you see that you have atom like this, and you have a second atom like this. So when you talk about the size of one atom, you talk about two things: non-bonding atomic radius, and you talk about the bonding atomic radius. So non-bonding atomic radius, that means the size, the radius, the size of the atom when it stands in the gaseous phase and without the chemical bonding with another atom. So it stays alone, freeze in a gas phase. The bonding atomic radius representing the size of the atom in a chemical bond, in a chemical component, in a chemical compound. So by understanding, you see that later when you learn about the bonding theory, you have two atoms. Let's say the atom A and the atom A like this. When they are freeze, it have the non-bonding side like this one. And then you put it close each other, and it means it make the bonding. So later when you learn the chemical bonding theory, you understand that you have the overlapping of the two orbitals. So when the two orbitals overlap, that means the distance of the nuclei will get shorter. So if you take the nuclei distance, in this case, you divide by 2, you will get the bonding atomic radius. That means the radius in one chemical bonding. Why for the non-bonding one, you take the size of the atom when it stands freely. That means the electron move in the maximum freedom. And you can understand, you can imagine that the non-bonding atomic radius will be larger than the bonding atomic radius. That means when the atom get in bonding, the distance will get shorter. Okay? So by this meaning, if you take the case of carbon or the case of yes, nitrogen, or let's say we take the K of carbon, it's easier. Take the K of carbon, okay? You will have free carbon. So you have non-bonding radius. It will make the carbon-carbon single bond. So you will have a bonding radius 1. We can say the carbon-carbon single like this. It will make also the carbon-carbon double. Then it will have bonding radius DC double like this. And it will have also carbon triple bond. So we have DC like this one. D carbon. So you can understand very well that when you increase the bond order from the single bond to double bond and triple bond, the distance will get shorter. So you can understand that the D non-bonding will be larger than the D single and larger than the triple bond. It says that the non-bonding atomic radius will be fixed and it changes from one element to one element. But when you take the same element, the bonding radius depends on the nature of chemical bonding. The same carbon can give different bonding atomic radius in different chemical bonds. You can see that the same carbon in a single bond, carbon-carbon bond, will have larger atomic bonding atomic radius compared with the carbon, the same carbon, but in the double carbon-carbon. Can you get what I mean?
Yeah.
Okay. So here you see the chance in atomic radius. So here we talk about the non-bonding radius, okay? So when you go from the right side to the left side of one row like this, from here to here, you will see that you increase the size of atom. And when you go down from top to the bottom, you will see increasing of the atomic radius. Talking about this one, it's quite easy. So here you have one add 2. Here you have helium, 2 add 2, 2b6. And here you have neon, 3 add 2, 3b6, like this. So you see that when you go from helium to neon, it will have one layer more. So the side will, like, you have one layer like this, nuclei, and then you add one more layer for the 2b. N equal to 1, N equal to 3, 2, and then here you have N equal to 3. So you can see that the radius increase by this way. Okay, easy to understand. We go from the top to the bottom of the table in one column, the size will increase. How about in one row? Anyone can explain why when you go from right side to the left side, the size increase, or when you go from the left side to the right side in one row like this one, the size will decrease? Anyone can explain? Yeah, please, Hung.
So I think because when we go from the right side to the left side, the left side to the right side, the atomic radius decrease because there's an increase in number of electron, but the same number of shielding. So the effective nuclear charge will increase as we go from the left to the right, and therefore smaller atomic radius.
Yes, thank you, Hong. Exact. So the number of electron setting will be the same. The core electron, let's say you have nuclei here, and then you have setting electron here. The number of setting electron will be the same. When you go from the left side to the right side, then you have one electron, you add one more electron. Okay, so when you add one more electron, then you add also one more positive charge to the nuclei. So why the setting electron, the screening electron will be the same. When you increase the Z, so you have the same, you have Z effective equal to Z minus S. So the setting almost the same, and you increase the Z. So basically the effective Z will increase. So that means that the interaction of the outer layer electron and the nuclei will increase. So that means the size will decrease. Okay. Thank you, Hung, for that. Now, we look in the chance of ionic radius. So, faster than the parent atom. That means if you take sodium, you remove one electron, you will get sodium gas ion. The size will be decreased. That's because, let's say, if you have sodium, Z equal to 11. So you have electron configuration like this, 3s1. Now you remove one electron, so it's become Leon. So it's 3s0. That means now you have two layer of electron, two, and here you have three layer electron. So basically, you will have the neutral atom bigger than cation. Anions are larger than their parent ion. So basically here you have chlorides. If you get one more electron, you will have anion chlorides. The size will be bigger. Okay. Anyone can explain why when you change from the neutral atom to the anion, the size will increase?
Is it because it either creates a new layer or makes the layer that already exists bigger?
Sorry, Bill, can you repeat?
Is it because when you add an electron, it either creates a new outer layer or makes the layer that already exists bigger? Maybe
this is the size increase, the volume, I mean the space volume increase. So okay, let's explain. You have a chlorides, okay? So the outer layer is 2s2 2p5. You add more electron, it become 2s2 2p6. So basically, you will have the same number of layer. You get what I mean?
yes.
You have the same number of layer. So why the size of atom of anion still increase?
Well, because the layer is bigger, I guess.
I think because there are more electrons in the anions, so the force from the nucleus applied on the electron will decrease, making the radius increase.
Again, can you repeat? My connection was not very well, not very good at that time. Can you
Okay,
repeat?
so when the atom receives an extra electrons, the force
Mhm.
from the nucleus applied onto the electrons will decrease, making the radius increase.
Yes, thank you. So basically, the number of nuclei will be the same, right? The number of proton, the positive charge in nuclei will be the same. You add one more electron in the outer layer. So the interaction of the electron with the nuclei will decrease. And that's why the size of the atom, the anion increase. Thank you. So here, summarize a little bit the chance of ionic radius. You will see that when you go from the top of the column down to the bottom of column, it will increase the size because you add up one more layer. The same for the anion. And when you get the cation, the size will decrease. When you add electron to become anion, the anion size will be larger than the parent atom. Now, we have a concept of isoelectronic series. So the group of isoelectronic series is a group of ions all containing the same number of electrons. Doesn't matter you have neutral atom, cation, or anion. When you have the same number of electrons, we call isoelectronic series. For example, you have oxygen to minus, fluoride minus, magnesium to plus, atom to plus. All these spaces have 10 electrons. So we call now, if you compare a little bit the size of the spaces, you will see that when you move from oxygen to fluoride, sodium, magnesium, and aluminum, it will increase the nuclear charge. Okay, that means the number of the proton in the nuclei increase. So that make decreasing in the radius. Because the number of electrons will be the same, that means the number of the electron layer will be the same. So when you increase the nuclei, the charge in nuclei, the positive charge in nuclei, the interaction of this nuclei with the outer layer of electron will increase. So the size will reduce. So for example, the oxygen, you have only the main number Z. Oops, sorry. Sorry for this. Yeah. So here you have oxygen with the Z equal to 8, Z equal to 9, and D equal to 10, right? So you have positive charge 8, interaction with 10 electron outside. And here you have for the fluorides, you have positive 9, interaction with the same 10 electron, and here 10 is the same 10 electron. So you will see that interaction will get stronger and stronger when you increase stronger interaction. So of course, it will be decreasing of the radius. So it's quite easy to understand. So when you want to look at the size of the species, which are isoelectronic, when they are isoelectronic, you need to take care of only the nuclear charge, so the main number of the atom. So why the size of the ion is important? Because the size of the ion is important when you put it in device. You can imagine that people talk a lot about the lithium battery. So what could be the operation of lithium battery? So here you can see that you have one anode. You have one anode here. So you have in the anode, what do you have? You have here the layer of the graphite layer, and in between you have lithium metal. Okay, and then in the cathode here you have cobalt oxide like this layer, and in between you have also lithium positive charge, lithium ion. So when the lithium battery operates, that means you use this lithium battery to power your smartphone, for example. What will happen? In the anode, the lithium metal will remove one electron to become lithium cation ion. So the electron here will flow through your smartphone here, and it go to here. And in the cathode, you have lithium here. This one will go through the membrane, and here take one electron, cobalt oxide, to become nickel cobalt oxide. Okay, so we have this reaction happen. So you imagine that in this activity, the lithium in between the layer need to escape of the two layers. So it's not need to get out. Okay, and here when the lithium get in, it will need to go through in between the two layers of the cobalt oxide. Okay, so imagine that if we replace the lithium by another metal like potassium, with the size of potassium larger than the size of lithium. So like you replace something very small, teeny, to become something very fat. So you can imagine that the escape of the potassium from the two layers of the graphite will be slower. And then the insertions of the potassium in the two layers of oxide, cobalt oxide, is also very slow. So that means the flow of electron you have here will be small, because one electron you generate equal to one lithium or potassium escape from the cathode, from the anode, and insert in the cathode. When one lithium completely escape the anode and completely insert in the cathode, you will have one electron. So slowly the escape of lithium and insertion of lithium in the cathode is smaller value of the electron flow you have. So you can imagine that when you change from, you take the same cathode and anode, but you change from lithium to potassium, your battery will become very weak with a lower energy density, and then with the lower current density you can have, and when you need to charge it, you will need longer time to completely fill the potassium in between the two layers. Do you get what I mean?
Yep.
Yeah. So you see that's why people is working nowadays in industry. They work with lithium battery. Of course, a lot of researchers start to say that why not potassium, why not sodium, and why not magnesium? because lithium is extremely small, right? When you look, lithium is only below the hydrogen. Hydrogen is extremely small, so the lithium is very small. When you move from the lithium to potassium or sodium, the size will increase. So you will need to take care of the escape and removal and insertion of the potassium or sodium inside the battery. So the energy density and the rate of the charge and discharge battery will be increased. So even using lithium is very dangerous because lithium is extremely easy to be extremely highly flammable. That means when you expose to the oxygen, it will burn up quickly, and the reaction of the lithium with oxygen is exothermic, violently reaction. But because it's very small, so the insertion removal from the anode, cathode are very efficient. So that's why people try to find a way to protect well the lithium battery against the flammable phenomena, rather than trying to replace the lithium by other one, less flammable but less efficient. Okay. Of course, as I mentioned, nowadays several research laboratory and the R&D department at the several big company start to work on the alternative battery like sodium, potassium, or even magnesium. But the one you can find nowadays in the market is lithium battery. Even it's very dangerous in some point of view. And when I stop here, I would say that now for the future development, sustainable development, people are developing lithium battery. And maybe you heard that in Hanoi, VinFast start to run battery electrical vehicle, electrical bus. So lithium battery could be the future energy for the sustainable development. So people work a lot on inventing new battery with higher power density, faster charging, more stable. Let's say for the electrical sell out by VinFast, they says after 3 years, you need to replace the lithium battery, and VinFast will take care of replacing battery for you after 3 years. But it also say the battery lifetime is about 3 years. So if you can extend it to make it more stable for 5 years or 10 years, it will be excellent contribution to the sustainable development. But another question, maybe the chemistry guy and also the material science guy or energy department guy need to think about is, or even well department student guy need to think about is at the end of 3 years or 5 years or 10 years, how can you recycle the lithium? You see here, it's very simple drawing. You have cathode material, which is lithium oxide, cobalt oxide. You have an anode, is lithium carbon graphite. You have a membranes. You have all the protector. So at the end of using, after 3 years, 5 years, or 10 years, whatever, how can you collect the lithium? You cannot dispose lithium in the normal way because it's flammable, right? So how you can destroy it? One question. Not pollution to the environment, not pollute the environment, but more serious question is how can you recycle? You can collect lithium because lithium is very expensive. Okay, so that's the question. For the moment, I don't know how to do it, but I hope that some of you may be interested in this serious question, impactful question. Imagine that if you can invent a new technology to recover, let's say 90% of lithium in all disposed lithium battery, it can be excellent contribution to the society, to the economy of Vietnam, and also for the sustainable development of Vietnam. Okay, you get what I mean? It's a big challenge, and I think that some of you may want to take care now because you have 10 or 20 years to solve this technological challenge problem. Not next year, you will see the disposal of lithium, but next 10 years, that will be important question for our society. Okay, so here are some examples how we work when you change the size, but I will not go in detail. Now, we move to the next section. We talk about the ionization energy. So ionization energy of an atom or an ion is the minimum energy required to remove an electron from the ground state of the isolated gaseous atom or ions. So we talk about ionization energy of both atom or ion. For example, if you take the sodium gas atom, you remove one electron, it becomes sodium gas. You will talk about the ionization energy of sodium atom. You can imagine also that you have magnesium plus gas. You remove one electron, you have magnesium 2 plus gas. You will have the ionization energy of the magnesium 1 plus. So we say that here for this sodium, you talk about one energy ionization, but when you talk about the magnesium, you will talk about the magnesium gas, one electron plus magnesium plus. So you will talk about the first ionization energy, the second ionization energy. Okay, the first ionization energy, and you talk about the second one. You can, for the aluminum, you can talk about the third one and so on. So the definition is applied for both the neutral atom and the ion. But the important, we talk about the gas phase. Okay. So on the ion, the atom and the ion are in the gas phase. That's the important thing you need to remember. So, yeah, as I explained, the first ionization energy is needed to remove the first electron from the neutral atom. The second ionization energy is the energy need to remove the second electron from the gas ion. So I need to emphasize it because some of you will confuse that I saw in the last examination, last year examination. Some of you confuse the I2, this one. So some of you confused like this, but I2 by definition is this one. That means the energy need to remove the second electron from the first gas ion, but not the energy required to remove 2 electrons from the neutral atom. You get what I mean? So be careful with the terminology. So if you look in the variation in the successive ionization energy, you will see that the first energy here for the sodium, the I1, the first ionization energy is very small compared with the second one. For the magnesium, you see that the first one smaller than the second ionization energy, and the second one is extremely small compared with the first one. And you see the same chance here. So the first ionization energy is always smaller than the second one, the third one, and so on. This chain exists because with X successive removal, an electron is being pushed away from an increasing more positive ion, so it requires increasing more energy. So if you look in the periodic chains in the first ionization energy, you will see that from the when you go from the right side to the left side, the atomic radius increase. That means the size will get bigger. That means the electron get farther from the nuclei. That means the binding energy of electron with the nuclei is smaller. So the ionization energy gets smaller. So that's why when you go from the right side to the left side, the atomic radius increase, but the ionization energy decrease. Okay? Or you can say inverse. When you go from the left side to the right side, the ionization energy increase because the atomic radius decrease. The same thing when you go from the top down in one row or in one column, the size of the atom increase. So that means the interaction of the electron with the nuclei decrease. So that make decrease the ionization energy. Okay. So basically, if you understand and remember well the evolution of the atomic radius, the size of the atom, you can understand and predict very well the ionization energy. Remember that if the atom or ion, if the atom get bigger, that means electron, the outer electron, get farther from the nuclei. So that means the interaction of that electron with the nuclei get weaker. So it also means this electron can be easier to remove. So that means the ionization energy, that energy you need to put inside to remove this electron, get smaller. Okay. Now, the last thing we talk about the electron affinity. The electron affinity is the energy change that occurs when an electron is added to a gaseous atom. So you see that if you put the ionization energy and electron affinity, they are in opposite way. Ionization energy, that's it, the energy that you put inside to remove electron from the atom. Become gas ion. Here, electron is the energy that will change when one electron adds up in the atom to make an ion. Okay. So in terms of absolute value, the ionization energy is positive, and the electron affinity is negative. It represents how easy an electron gain how easy an atom gain an electron. So it has negative charge, negative value. Sorry. So we can say that the ionization energy is one endothermic process. Why for electron affinity? For the adding of electron to the atom is exothermic process. If you look the chains of affinity, different element in one table, in the periodic table of elements, you see that there are no obvious chains. If you take case of the hydrogen, you will see that when you go down, the affinity decrease, the affinity with electron decrease. It seems in a very good order for the 1A. Okay, this is something you can explain because the hydrogen is quite small. So this is 1s, 1. Here you have 2s1. So the distance with the nuclei gets shorter for the hydrogen. So if you add one more electron here, it becomes 2s2 is the adding of electron get easier. So we can say the affinity of hydrogen with electron affinity of hydrogen is stronger than the affinity electron affinity of lithium. But when you move to the second column, barium, arsenium, and calcium, is inverse. That means when you go down with the bigger size of atom, the affinity slightly increase. So it's exactly opposite with the first column. If you look at this column 6A of oxygen, you see that when you move from the oxygen to sulfur, the electron affinity increase. So that means the sulfur can easily can get to accept electron compared with oxygen. But then when you move from the sulfur to selenium, the electron affinity decrease. So you can see that it's not in a clear chance like what you can observe for the case of ionization energy. So to be short, the electron affinity representing how easy one atom can receive electron, and they have no obvious chance for different element in the periodic table of elements. We say that what you need to understand, you understand the concept, but you don't need, you can understand the concept, but you don't need to remember anything because there's no chance, so you no need to remember, so it's easier for you guys. So we go very quick today lecture. So here are a few key points we have learned. We talk about the development of periodic table of elements. The driving force of this development is try to put the element, which are very numerous now, more than 100 elements, in different columns, in different rows, in a pattern structure. So one can understand the similarity in terms of physical and chemical property of different elements, but not need to remember one by one of all the 100 elements. It's quite difficult to remember one by one. But now, when we have the table of elements, periodic table of elements, we learn the main chance about the evolution of the radius, about the size of the atom, how they evaluate when you go from the left side to the right side of the rows, when you go from the top to down in one column. And also you can remember the chance when you go from left to right or top to down of one column in terms of ionization energy and in terms of electron affinity. We learn also a very important thing. We learn also about the atom size and ion size. Remember about the concept of non-bonding and bonding radius. The non-bonding atomic radius will be fixed given value for X element. But the same element in different chemical bonding can have a different bonding radius. Okay, so when we talk about the bonding radius, you need to precise what bonding you are talking about, which bonding you are talking about. Okay, so today we can close our section here. Do you have any question? I run through quite quickly all the content of this lecture. Do you have any question?
Actually, could you explain again about the X-ray method to identify elements?
Okay. Okay, here we go. So you know that for X element, you have the Z number fixed, right? So you have a different layer of electron. So the first layer close to the nuclei, you call the K layer. the second one, L layer, and the third one is M layer. So this is the how to say, the way people label different layer of electron. So the distance, if you look at the distance between the electron in different layer with the nuclei, you see that electron case will get very close to the nuclei. The distance of the L layer will get longer, and the distance of the M layer is longer than L1. Now, if we consider about the binding energy of the electron with nuclei, the interaction, the strongest interaction is between the K electron with the nuclei. The second strongest one will be the L electron with the nuclei. And the third one will be the M electron with the nuclei. That's the binding energy. Now, in terms of potential energy representing how it can generate energy if it's moved, if you want. So the potential energy, that means the energy created by the position of electron with the nuclei. So if you put the potential energy, so if you can put nuclei here, then you will have the first layer is K, the second layer is L, and the third layer is M. It also says that the electron in the M layer, which is the outermost layer, far from the nuclei, have highest potential. It can easily to be removed. Okay. And the electron in the K level, K cell, because it's very close to the nuclei, so it have very low potential, but have strong binding energy with the nuclei. Now, if I remove electron from the M layer, this one, so the energy I need to put here is equal to ionization energy. Okay, but this is not the purpose of this X-rays method. In the X-rays, you use very high energy input to remove the core electron, the electron in the case. So you get is remove. Okay, you send high energy input. Okay, so this electron remove, it will create a vacancy. Normally occupied by electron now become empty. So the tendency is as the electron here in the second layer with higher energy will fall down to fill this empty position left by electron. Because the L layer electron have higher potential energy. So that when electron fall down by this way, it will emit energy equal to L minus K. Okay, so here you will have X-rays emission. But not only electron in the K will fall down, the electron in the M also fall down, right? And then you will have a second emission equal to M minus K. So if you collect this emission, you will have a spectrum like this one. You have the first emission and the second emission. Okay? So here you have energy emission. So by looking these two emissions, you know which emission correlate with which electron falling down. And then you would know what is the nature of this atom. Because we have a different arrangement of KLM, different number of electrons. So at the end, it will have a different X-rays diffraction pattern. Am I clear?
Clear.
So let's say if someone make an object by gold, someone make gold, and then they put, let's say, 1% of wolframs. So you have gold wolfram. Now your customer want to ask you whether the object is 100% gold has impurity. So you will use this object, you put inside the X-ray diffraction. So if the X-rays emission spectrum have only the pattern of gold, then you say that the object is 100% of gold. But if you have the pattern like this, here you have gold and here you have tungsten, so you can say, you can confirm clearly that the object is not pure, it contains tungsten like impurity. Okay, so nowadays people are using it to quantify, to do the characterization of the mineral from different and different object, high value object, to see whether it's make a pure element like gold, platinum, or it have some percentage of impurity. Okay, because each atom will have characteristic X-rays pattern. Any other question?
Can I have a question?
Yeah, please.
How can you make sure that the radiation will remove the core electrons? I mean, the outer, is there any situation that it will remove the outer electron because it is cover the outer layer, and it also needs smaller energy to be ejected?
Yeah, for sure. Sure. So to make sure that you can remove the core electron, you need to send a beam incident, this incident radiation with the very high energy. So you can remove the core electron. But if you send the incident radiation with low energy, then you remove only the cell electron, the outer electron. Okay, so let's say you have the law of energy conservation. So you have incident electron, energy, incident. So when you inject the incident energy, the electron will fly out. Okay, and when it fly out, you will have a kinetic energy of electron. So the incident energy input equal to energy kinetic of electron plus the energy binding between electron and nuclei. Okay, so the kinetic energy, that means the electron fly out, you can do the measurement to know what could be the kinetic energy of electron get out. And you know the energy you send in the incident radiation. So by doing abstraction, E incident minus E kinetic, you know the E binding, right? So you can, for different atom, the binding energy will be different. So you should send different incident energy. You get what I mean? So to be short, to make sure that you can remove the core electron, you need to send high energy. How can you know the electron fly out is core electron or cell electron? You make the measurement of kinetic energy. So if you send the same energy radiation, the core electron will get out with smaller kinetic energy. The cell electron, the outer layer electron will fly out with higher kinetic energy. You get what I mean? Of course, both the core electron and the cell electron will be removed at the same time. Am I clear?
Yes, thank you. Yes.
Okay. So that's why when you want to do the X-rays characterization, atomic X-rays characterization, you need to use very high energy beam. If no more question, I have one important message to tell you. So as I mentioned in the introduction lecture, after this lecture, we will have a midterm test. So next Wednesday, you guys will have a midterm examination. No class, but midterm examination. Okay?
So it's on 15th of December. So on next Wednesday will be the midterm examination.
Yes.
Okay.
So the midterm examination will be on the basic of multiple choice question as we work sometime during the lecture, and it will be in the Moodle. Okay. So prepare on that. It will have about 1 hour and a half with about 60 questions or 40 questions. I will see how I will arrange the list of questions. But very probably it will have between 40 to 60 questions for 1 hour and a half. And the question will be multiple choice. Okay. So after you finish the test, we know rapidly the score.
Wait, so what is the topic, what we have to practice for the test?
About all the topic we have learned from the first lecture till today lecture. That means a periodic table of element. Okay.
Right.
I please, because I've seen that you only upload the slide from you haven't uploaded the slide since the fourth.
Oh, sorry for okay. Sorry for that. This afternoon or this evening, I will upload on the slide. That missed because last 2 weeks I got some trouble, some issue with my family suffer due to the loss of my mom. So it's terrible time for me. I will not. I do not concentrate fully in the work. So I will upload on this slide by today evening, no later than today evening. Okay.
Professor, thank you.
Thank you for that. Thank you for understanding. Okay. If no more question, thank you. And hope you will.
I'm sorry, may I ask you a question?
Yeah, please.
Yes, based on the midterm test, but I want to ask if we are allowed to, bring along our periodic table.
Okay. So basically, for the periodic table, I will provide you with the very simple one, the one that you can use to answer the question. So other than this document, the simple periodic table of element, we will provide to you. No other document are allowed during the test. Okay. Is it okay?
Yes, it's okay. Thank you for explaining.
It's okay. Thank you so much. Bye-bye.
Bye, Professor. Goodbye.
Bye, Professor.
Bye, Professor.